Welcome to my YouTube channel. In this video we are going to be looking at practical problems under gravitation. So in our previous video, which is the part 1, we derived some of the formulas that will be needed in solving problems under gravitation. So in this part 2 we are going to be looking at practical problems. So let's dive in. So the first problem we are going to be looking at is given as this. So a 1000 kg satellite orbits the Earth at a constant altitude of 100 km. How much energy must be added to the system to move the satellite into circular orbit with altitude 200 km? Now this problem tells us that the satellite is already in orbit, which is 100 km. So from that 100 km, you want to move it to another altitude, which is 200 km from the surface of the Earth. So the question is, what is the energy needed to move it from 100 km to 200 km? There are several ways you can solve this particular problem, but the easiest way is to look for the mechanical energy, or which is the total energy for this orbit, for the satellite in this orbit, and the mechanical energy for the satellite in this orbit, and take the difference, and that gives you the energy needed that must be added, or the energy that must be added to the satellite to move from this orbit to this orbit, right? So let's dive into the formula for the mechanical energy for a satellite in an orbit. So the mechanical energy is a combination of kinetic energy plus potential energy, which is equal to this formula. And this formula was derived in our previous video, part 1, where G and E, they are gravitational constants, mass of the Earth, the mass of the satellite, then this R is the distance from the center of the Earth to the points above the surface of the Earth that you are considering, right? Okay, so we know that the mechanical energy for the first orbit is going to be written as this R1, which is 400. Then the mechanical energy for the second orbit is going to be Me2, which is this. So the difference between this and this will give us the energy need that must be added to move it from the lower orbit to the higher orbit, and that is given by energy equal to mechanical energy 2 minus mechanical energy 1, right? So what is this particular one? Is this one minus this one. So let's see how it goes. So we have this minus this, so which can be written as plus. So we can factorize and simplify this expression so that it becomes GMEM all over 2, then 1 all over R1, because this one is plus, it comes to this side, minus R2. So this one can come here, this one can come here, all over the multiplication of these two. Then also note that your capital letter G multiplied by capital letter M subscript E is also known as small letter G, capital letter RE, that's radius of the Earth. Okay, so this is what we now have, and we can also move further by simplifying it in this form. So let's substitute the values of these parameters that are well known. So we have 9.8 radius of the Earth. Remember to always convert it to meters. Then the mass of the satellite, which is this, divided by 2. Remember that the radius, so this R2 and R1 is the distance from the center of the Earth, which is the radius of the Earth plus the altitude for R1. Therefore R2 is the radius of the Earth plus the altitude in kilometers. So when we add this and this, remember we have to also include the 1000, which is the kilometer. So which brings us, so if you solve this particular expression here, it gives us this one. Then R2 is 6600 times 10 raised to power 3, which can be converted as this, while R1 is 6500 times 10 raised to power 3, which is same thing as 6.5 times 10 raised to power 3. Then we have this. So at the end of the day, we have the energy that must be added to the satellite at lower orbit to move to higher orbit, which is this. Now let's look at another problem which is giving us this. What is the escape velocity of a satellite at an altitude of 820 km in a circular orbit about the Earth's surface? So if you understand this question properly, you realize that the satellite is not on the Earth's surface. It's already in an orbit which is 820 km. So we are asked to find the escape velocity from that orbit, not from the Earth. So we are going to solve this particular problem. Use the general formula of conservation of energy. So K1 plus mu U1, that's kinetic energy, plus potential energy in that orbit, equal to kinetic energy plus potential energy when it is moving towards infinity, away from the Earth's surface. So remember, the kinetic energy, we need to calculate the speed needed to launch that satellite into infinity. So the kinetic energy is going to be half of mv squared. The potential energy is going to be our usual term, which is minus gmem all over r. The r there is the altitude 820. The kinetic energy when the satellite goes to infinity is going to be 0. The potential energy when the satellite goes to infinity is also going to be 0. So in that case, we have this expression. So this minus this equal to 0 plus 0. So if this one comes to this other side, it becomes this. So we can make our V the survey formula, and that gives us this. Now remember that your Gm can be replaced with what? Guess it right. G capital letter R E squared. And remember, this your R is the radius of the Earth plus the altitude. So we have this particular expression. This should be our final expression. Then we can make our substitution and solve for V. This is the radius of the Earth. You square it, acceleration due to gravity. This one is the radius of the Earth plus the altitude, then multiply by the kilo, which is 10 raised by 3, and that gives us. And so this is the speed needed to send the satellite from that orbit to infinity. That's to escape to infinity, right? So let's look at another problem, the third problem, which is giving us an Earth satellite moves in a circular orbit with an orbital speed of this. Find the time of one revolution. To solve this problem, remember that there is a formula that connects period, velocity, and the radius, and which is giving us t equal to 2 pi r all over v. We are asked to calculate t, we are given v, but we don't know our r. Now, we must find a way of getting our r. Remember, when a satellite is in an orbit, right, the particular speed for that satellite in that orbit is tied to the altitude, r. So for a particular speed, there is a corresponding r. So we can get the r from that speed, and the formula needed is giving us this v, which is the speed of a satellite in an orbit. Remember that is given by this expression, which is also equal to this expression. So from this expression, we can make this r the survey formula by sending r to this place, or we take the square out first, becomes squared, r comes here, v goes down, and we have this expression here. So from these points, we can even decide to substitute r as this inside here and go ahead and solve for our t, or we calculate this one, then finally substitute into this part. So let's see. We have our r equal to this. I think it's easier to solve this one direct. Then r equal to what? 1.6 times 10 raised by 7 meters. So we can now substitute into this part here and get our t. So our t is equal to 2 pi this distance all over 5,000, then our T is equal to 20,177 seconds, which can be converted to what? 5 hours 6 minutes. And that's it. I hope this helps. Please like, share and subscribe to this YouTube channel so that you can get to see more contents. Thank you.